I apologize. What I would like to discuss is singular spaces or spaces with trivial canonical singularities. And I would like to extend some of the results that are well known for manifolds to the singular case, and I would like to explain why I think this could be interesting. So before starting, let me just recall a few of the fundamental results that we know for manifolds, and then I'd like to explain how to extend those to the singular case. So this is spaces with trivial canonical class. And maybe one of the most fundamental results is a decomposition theorem that exists for spaces or manifolds with a vanishing first Chern class. So X, a projective manifold, C1 of X is assumed to be 0. And the statement is that up to étale cover, X is a product of an abelian variety, an irreducible complex symplectic variety, and a Calabi-Yau. So there exists an étale cover and a decomposition which is X twiddle is abelian times a couple of complex symplectic times a couple of Calabi-Yau. So Bj irreducible complex symplectic and Ci Calabi-Yau. So this is one of the results that we were interested in generalizing. There's another one which maybe will feature more prominently today, which is a characterization of quotients of abelian varieties. Namely, again, X, a projective manifold, H ample, and what do I need? I need C1 of X times the appropriate power of H is 0, C1 of X squared times H is 0, and C2 of X times the power of H is 0. Then, so X is a quotient of abelian. These are two very fundamental results, and what I would like to do is generalize them to the setting where X has singularities as they appear in the minimum model program. And let me give the results right away and then discuss why I think that could be of any significance. So generalizations. So here's the first result is when X has canonical singularities, canonical projective variety, and so Kx is numerically trivial, then we can do a similar thing but infinitesimally. What we can do is we can find a cover which is no longer étale, but it's étale away from the singularities. So there exists a quasi étale, say X twiddle over X, and that means étale over the smooth locus, and a decomposition of X twiddle into an abelian part and a part Y, which now summarizes the complex symplectic and and a Calabi-Yau thing that we have. But what we have is we do not have a decomposition of y into these factors. What we can decompose is a tangent bundle of y. So as well as a decomposition where the tangent sheaf of y is a direct sum of foliations where A, the EI are Lie closed. That is foliations, and B, the EI are stable with respect to any polarization. So if X is smooth, then the EI are, of course, the tangent bundle of the BJs or the CIs. Yep?
Do you see some shadow or is there a kind of foliation that looks like coming from it?
I'm going to mention this in a second. First, let me say, or immediately state the generalization of this result here. And here I will say very little, except that in the singular case it just works. So the characterization of torus quotients just works for terminal varieties. So in a sense, if you wish, you can see this as saying that the foliations that you have here are integrable. I mean, if you have a torus quotient, then on a quasi-étale cover, the attention bundle will split into a direct sum of line bundles, which corresponds to the EI here. And that is a trivial case, if you wish, where the foliations here are integrable. And you could interpret this result as saying that the second Chern class is an obstruction against algebraic integrability of the foliations. I don't know how to make this precise, but that seems to be the philosophy here. And yeah, today I'd like to concentrate on this result, but before doing so, I should answer Christian's question, or what I believe Christian wanted to ask. I stopped him short. So why are we doing this, and why would that be of any interest? Is this a generalization for generalization's sake? And of course, I want to convince you that no. The idea is, I mean, how do you find a variety where the canonical class is numerically trivial? You start with a variety, an element of the much larger class of varieties that has Kodaira dimension 0. Kodaira dimension is the natural invariant in birational geometry. Then apply the minimal model program, and if everything that is conjectured in the minimal model program works, you will end up with a minimal variety that has first Chern class 0, but of course you have to pay a price. It's going to be singular. Now, if you allow me to be, for 1 minute, to be a little megalomaniac, then by the end of all days, what we're heading for is something like a bit of a structure result for varieties with a first Chern class 0. Similar to the decomposition theorem that exists for smooth manifolds. If everything would work fine, then you start with your variety of Kodaira dimension 0, apply the minimal model program, and you come to a variety where this decomposition applies. And if you're extremely optimistic, there are some Americans here, so maybe I'm allowed to be optimistic, that could eventually induce a decomposition of the space itself. And that would be a structure result for varieties of Chern classes 0. And no matter what eventually comes out of this program, so it seems to us that one of the fundamental building blocks would then be varieties, terminal singularities, first Chern class 0, where the tangent bundle has only one summand, and this summand is stable with respect to any polarization. So that should be a building block out of which all the others are composed. And no matter what the structure theory eventually entails, these will be important varieties. I think that's for sure. And I think it will be very interesting to describe them. And to answer Christian's question right away is if you look at these building blocks, then we can see in dimension no more than 5, which is due to our restrictions, our knowledge of linear algebra. If the dimension is no more than 5, then these building blocks come in 2 flavors, which are irreducible, symplectic, and Calabi-Yau. So there seems to be something interesting going on there, which I think is the rationale why this might be interesting. Now, let me stop the advertising and stop being megalomaniac. Pardon? It has only 2 reflexive forms, a 0 form and a top form. Whereas a symplectic has the symplectic form out of which any other form is generated. Pardon? Huh? Oh. Actually, nowadays it's only the Americans that do that when they visit. Huh? Why? No, never. I don't understand the question. The tangent bundle of Y decomposes, or the tangent sheaf, I should say. Y is singular. Yeah, it's a direct sum of reflexive subsheaves that are closed under the Lie bracket. Oh, I missed one point. C trivial determinant. Okay. Yeah, the stability is preserved if you pass to further quasi-étale covers. Okay, so yep. Do we have simple examples of irreducible Y's like, I need to think a little. Give me some time. Okay, the answer is yes, but I would rather give my talk now. Yeah. Right. So I would like to give an idea how to prove this. And I mean, in the classical setup, what are the buzzwords here? It's a lot of analysis, existence of metrics, flat sheaves, and eventually the fundamental group. So in order to give an idea how to prove this, I should discuss the fundamental group a little. So this is the fundamental group. And essentially the question is this. So given a quasi-projective variety X, how do the fundamental group of X compare to the fundamental group of the smooth locus? So how do, and really I want to discuss the algebraic fundamental groups. So and pi 1 of X reg compare. And examples show they're generally not equal. But there's something that can be said about this. So we know, of course, there's the inclusion map. of x reg into x, and that gives a morphism of the fundamental groups and then a morphism of the algebraic fundamental groups. And this is well known to be surjective, but we know almost nothing about the kernel. So this is essentially what I want to study here. The only problem is that our result, as far as we know, has no formulation in terms of, well, the kernel of this inclusion morphism is something. The result that we have is formulated a little differently. It goes as follows. So x quasi-projective KLT, and given a tower of quasi-étale morphisms. So we have x is y0, y0 is covered by y1, covered by y2, covered by y3, and so on and so on. I'm looking at such a tower. I'm assuming that all the gamma i's are quasi-étale, and I'm assuming that any of the y's is Galois over x. So where all yi are Galois over x, then what we can show is that in this tower of morphisms that are quasi-étale, and I should say plus surjective, then almost all morphisms are in fact étale. Then almost all gamma I are étale. So quasi-étale means étale away from the singularities. So, or you could say unbranched in codimension 1. So, right. I will say about the proof of this result, I will say next to nothing. Instead, I would like to spend the time that I have basically explaining the meaning of this result and its application. So let me just, for a proof, let me just mention that if you have isolated singularities, then this result is not ours. That has been shown by Sheng Yang. This is the finiteness of the algebraic local fundamental group. If the singular set is not isolated, then it's a complicated induction process that uses Sheng Yang's result as a start of the induction and proceeds by building a suitably constructed Whitney stratification on your space. So maybe this is first remark for isolated singularities. Remarks. For isolated singularities, this is due to Xu, and in general, the proof uses Verdier's results on the topological triviality of algebraic morphisms. So to construct a Whitney stratification, and then proceeds by induction. Last remark, what I mentioned already earlier is not clear to us if there is a formulation that is formulated in terms of the kernel of the push-forward map here. So unclear if result can be formulated in terms of the kernel of the map iota. And last remark is this is not the best result that we have. There's a more general version of it where the morphisms gamma need not be surjective, but this is more complicated to formulate, so let me skip this. So we have a version where the gamma I need not be surjective. So these are remarks about the proof. And now let me say, or start out by saying how this result can possibly be applied to give something useful by mentioning one trivial corollary that comes out of this. So corollary is X as in the theorem, then there exists a quasi-étale X twiddle over X, actually Galois if you wish, such that the algebraic fundamental group of the smooth locus and the algebraic fundamental group of X twiddle itself are isomorphic. And the proof is easy. Assume we start with X. So proof. So this is an X twiddle rag. So on X twiddle, the algebraic fundamental group of the space and its smooth locus agree. So the proof is easy. So if we have this equality already on X, then there's nothing to do. So if pi 1 of X rag is not isomorphic to pi 1 algebraic of X, well, that means that pi 1 algebraic measures étale covers. That means that there's an étale cover of the smooth locus that does not come from an étale cover of X. So we have an étale cover of the smooth locus that does not come from an étale cover of X. On the other hand, if I have an étale cover, or in fact any finite morphism, then I can always close it up to a finite morphism that is defined over all of X. So I start with an étale cover on X vec. I close it up to a finite morphism over X. But since this cover does not come from an étale cover of X, what I get when closing up is a quasi-étale cover that's not étale. So assuming that the fundamental groups are not the same, I get a cover, so which is say x1 over X, which is quasi-étale, but not étale. Okay, now I iterate this process. Again, I ask on x1, is it true that the algebraic fundamental group of x1 is the same as the algebraic fundamental group of the smooth locus? If no, I get another cover. And eventually, I construct a tower of covers which are quasi-étale but not étale. And our theorem says that no infinite tower exists. So this process must stop after finitely many times, which is to say that then every étale cover of the smooth locus comes from an étale cover of the space. So the algebraic fundamental groups agree. So iterate this process. And the theorem asserts that this iteration terminates after finitely many steps. You have to take Galois closures in every step, and or if you're smart, you might notice that if you take a cover that's associated with the algebraic fundamental group, then you're good already. So, and so iterate this process, and the theorem asserts that the process terminates after finitely many steps. So this is essentially the meaning of the theorem. There is a quasi-étale cover where you can't see the difference, or where the difference between the algebraic fundamental groups vanish. And that has, of course, all sorts of desirable properties. And there's a bunch of applications here. If I have time at the end, I will probably mention a few. But for now, let me look at the main application that I'm interested here. This is this characterization of torus quotients. And for that, I need to discuss flat sheaves on singular spaces. So this is the next section of my talk, which is, I lost track, this is 3. Flat sheaves on singular spaces. So the setting I would like to discuss is the following. I have X, a quasi-projective KLT variety. And I have F0, a flat sheaf on the smooth locus. I should explain what I mean by this, because there's 2 ways to define flat sheaves on smooth manifolds. One is using connections and maybe D modules, which does not generalize well to the singular setting. And one is representations of the fundamental group, which is, of course, what I'm going to use here. So by a flat sheaf, I mean an analytic sheaf, not necessarily algebraic, locally free, and given by a representation of the fundamental group of the associated complex space. And we are working overseas, so when I say analytic space, I don't mean Berkovich or nothing scary. So, right. So this means, so F0 is a locally free analytic sheaf. I should say, to be precise, on X reg and the associated complex space or complex manifold, which is given by a representation, say, rho of pi1 of X reg, and to be precise, I should say complex manifold to some GLN. So this is the space, this is the setting I would like to consider. And that has been considered by many people in the past, of course. The most fundamental result is Deligne, I guess. Deligne says that, is there someone smiling? This sheaf has an extension as a coherent sheaf on X. So F naught extends to a coherent, I should say again, analytic sheaf on X. I mean, normally, if you have an analytic sheaf that's defined away, if you have an algebraic sheaf that's defined away from a subset of codimension 2, it's a no-brainer to extend it to a coherent sheaf. Algebraic sheaf on X. In the complex world, this is terribly hard. And for flat sheaves, the linear shows us how to do this. So in particular, if our variety happens to be projective in the first place, that means that the flat sheaf, which initially is an analytic object, happens to be algebraic. This was what Deligne was heading for. And right, so what I would like to say is there's something we can say about the Deligne extension here. Extends to an analytic sheaf. I should probably give it a name, F on X. So the main observation is if we are in a setting where the algebraic fundamental group of X reg is the same as the algebraic fundamental group of X, then F is again flat. Flat, that is in particular locally free. Let me spend a minute to say how to prove this. If I'm allowed to ignore the, it's such a small symbol, is it? If I'm allowed to ignore the algebraic fundamental group, and just if I have the statement about fundamental groups, then of course this is easy. What I have is I have a representation of this group, and I need to extend it to a representation of this group. And if the two groups are the same, then okay. There's nothing to it. Unfortunately, we do not know that these two groups are the same. We only know that their profinite completions are the same. So there's something profinite going on here, and there's some extra input that we need. And that input comes from, I guess it's fair to say that it comes from mathematical logic. And this is Maltsev's famous result about finitely generated linear groups. So let me recall what that was. So let me prove this observation. So observe, we have the image of the representation map that takes the fundamental group of X reg into GLN. This is a subgroup of GLN, of the general linear group, about which we know that it's finitely generated, because the fundamental group is finitely generated. For instance, you could triangulate your manifold and then realize that the fundamental group is generated by the what do you call this, one-dimensional simplices in your skeleton. So this is finitely generated linear group. Hence, and this is the famous result of Maltsev by Malchev. What was the word? It's residually finite. Thank you. Okay, I forgot the word. What does residually finite mean? It means that the profinite completion morphism is injective. So that is the map of image rho into its profinite completion. So this is injective. And interestingly, this is enough to extend flat sheaves. So let me explain why by just drawing all the groups that we have, and then we draw all the profinite completions and then lots of arrows between them. So here's the main player that we have. That map has two morphisms. First, there is the morphism 2 pi 1 of x, the inclusion map, which is known to be surjective. And then there's the representation map rho. Right. And for each of these three groups, I have the profinite completion. So there's pi 1 of x reg completed. There's pi 1 of x completed. And there is the image of rho completed. And I have the completion morphisms. And I know this completion morphism here is injective. Now, taking profinite completion is a right exact functor. So we have a surjection here and a morphism here. And by our assumption, we assume that this is isomorphic. So what I immediately, you don't look happy. No? There's a hat missing. But I don't know your name in the yellow pullover. Yeah. Something's wrong? No. Okay, you're good. So, right, we have. Okay, now we see immediately what to do. I have pi 1 of x here. I'd like a representation, please. And what do I get? I get a morphism here. This is an isomorphism, so I can go over here and compose with this map. Get a map here. Right. There's more I can say, because this map is surjective. Any element here is represented by some element there, and then the image is the same as going here and going up. So what we can see is that the image of pi 1 of x lives in the image of this injective map. This map being injective means that the image of this map is the same as the friend down here. So this arrow extends all the way down there by using that the image of this arrow and the thing here are the same. Now Vlad is looking unhappy. Well, you're making wrinkles.
I'm making wrinkles because Simpson's result, I'm actually thinking about something else. Simpson's result valid. Is it valid on the singular space?
We're coming to this in no time. This is actually the next section. Yeah, right. So So I have found a representation of the fundamental group of X, just knowing that the algebraic, the profinite completions are the same, and therefore I can extend my flat sheaf. So bottom line is we obtained a representation of pi 1 of x that induces rho. So what was that? So we obtain an extension of the flat sheaf to a flat sheaf, which is in particular locally free. So in a sense, if we are working on a space where, let me summarize the bottom line. If we're working on a space where we know that the algebraic fundamental group of the space and of the smooth locus are the same, then what we get is we get for free that the linear extension of any flat sheaf is automatically locally free. This is what I'm going to use.
There is no restriction on the singularities in this theorem.
No.
That's exactly my question, which I was asked. I mean, so is the Simpson's theorem?
No, but for terminals it does. And this I'm going to explain now. So what Vlad is asking, and what I want to say next, is that this implies that pretty much any flatness criterion that you find in the literature, like he's quoting Simpson's result, there's also Donaldson's result, which is maybe what we're going to use, just works for terminal spaces. That statement is, of course, to be taken with a grain of salt, but let me make a precise statement using the Donaldson formulation. So let me formulate this as a corollary. So the flatness criteria that you know just work. And I'm using the flatness criterion that was on the board already when we talked about the characterization of abelian varieties. So, and this is essentially this. Corollary. So X, a quasi-projective terminal variety. I think I need projective. Sorry for that. F, a reflexive sheaf such that C1 of F times h to the n minus 1 equals 0. C1 square of F times h to the n minus 2 equals 0, and C2 of F times h to the n minus 2 equals 0 for h ample, for one ample h. Then we have two statements, F restricted to the smooth locus is flat, and second statement is there exists a quasi-étale cover, say gamma from x twiddle to x, such that the pullback of F, and then I don't want any torsion in there, so I take the reflexive file, and this is flat, in particular locally free. In particular locally free. So this is the question. This is essentially Donaldson's result for terminal spaces. And let me again sketch briefly Simpson. Yeah, Simpson usually involves an extra Higgs bundle structure, which we take here to be trivial. Okay. Sure.
So in your setup, X was scale of T.
Yeah, now I'm looking for terminal, and I'm going to explain why I'm looking for terminal here. The question is, what is a second Chern class? For a singular space, a Chern class has been defined, I guess, by Goreski-McPherson. And no matter what the definition is, I'm not sure I understand it. It's terribly complicated. If I have a space where the singularities are in codimension 3, then defining the second Chern class is easy. Because I really just look at these intersection numbers, well, general complete intersection surfaces, and they will then stay off the singularities. So if we're working for in the general setting like normal varieties, I wouldn't know what the formulation of the statement means. For terminals, it's clear. Yeah. You. Yeah. Yeah, terminal is a subset of KLT, so
what is your assumption? Terminal, not KLT.
in this corollary, the assumption is terminal, and therefore I wrote terminal.
But I'm not talking about this corollary. I'm talking about
Yeah, until now we have been, everything was fine for KLTs, but now I specialized to terminal.
why is the Simpson result? That was my point. Why is the Simpson result valid for KLT?
You never said that.
I don't want to say this because you would have to think what it actually means.
No, because, look, your assumption is KLT. Then you define observation with something false. For this assumption,
Yeah.
is the assumption KLT or terminal?
The assumption is KLT. This observation is true in general. But this corollary works under the additional assumption. So far, everything was perfectly fine for KLTs.
But could you make this work for KLT, assuming?
Yes.
So
that's the
only thing you need from terminal.
Yeah. Right. Yeah.
Then that would be a stronger.
That would be a stronger statement, and that's the way we formulate it in our paper. But it doesn't look like a very nice statement. So from the point of view of minimum model theory, terminal is a very natural class anyway, isn't it? When have you ever met a KLT singularity that happened to be in the wild? It doesn't show so often. All terminals, exactly. Yeah. Right. Okay. Let's. I have 3 more minutes. So idea of proof. No. We started 2 minutes late. Idea of proof is, of course, choose a general, complete intersection surface S for H, then F restricted to S is locally free and has vanishing Chern class. So, by your favorite flatness criterion, whether it's Donaldson or Simpson, that means that F restricted to S will be flat. So, F restricted to S will be flat. So, on that general complete intersection surface, here are some singularities. We have found a flat sheaf. So we have found a representation of pi 1 of S. Now, a second is Goreski-McPherson. They prove that pi 1 of S is the same as pi 1 of X reg. So that means a flat sheaf is a representation of the fundamental group. That means that we have found an extension of F restricted to S to all of X reg. So so have a flat extension G of F restricted to S to X reg. Third step is if you have 2 reflexive sheaves and they agree on a high enough degree hypersurface and they're the same. Now there's a catch here because the word high degree depends on the sheaves. So you have to give an a priori estimate of the degree that you need by invoking the word bounded families, because some Chern classes are bounded. But this logic issues aside, so let me say, since degree of h is high, this means and g restricted to S is the same as f restricted to S, we get that f is G. So this proves part one that f restricted to the regular part is smooth. And then, of course, part B, we have already seen, and it was the observation, if you pull back to a model where the difference between the fundamental groups vanish, then your extension will automatically be flat. And then, now I think it's only 1 minute. How does this apply to the characterization of torus quotients? Well, you apply this theorem with f being the tangent sheaf. F being the tangent sheaf, then if f is the tangent sheaf, then the assumptions here reproduce exactly the assumptions of the torus quotient characterization. So what we see is, in B, we get a model where the pullback of the reflexive pullback of the tangent sheaf is flat. But what is the reflexive pullback of the tangent sheaf if we are talking about an étale or quasi-étale morphism? Is the tangent sheaf upstairs? So that means the tangent sheaf upstairs is flat. In particular, is locally free. And then there's this problem of Lippmann-Zariski that has been solved for singularities as they appear in the minimum model theory. If you have a KLT, or I think now due to Druyel and Graf, if you have a log canonical singularity and the tangent sheaf is locally free, that means your space is smooth. So that means the space is smooth, x twiddle is smooth. So we already have quotient singularities. But better still, on x twiddle, the tangent sheaf is flat. And then you have the classical characterization of torus quotient that gives you that x twiddle is a torus quotient. And there you go. Thank you. So the honest answer is I don't know what to believe. Of course, we would like to show that these foliations have algebraic leaves, but the state of the art is light years away from being able to prove this. And this is another reason I would like to go to Brazil next year. No, the Bourvil-Bogomolov proof involves holonomy arguments and then existence of metrics. And in the singular case, again, the technique seems nobody's able how to do this. So what we do is we mimic a very old attempt of proof made by Bogomolov by analyzing the ring of differential forms. So we do not use any metric arguments here. We would love to, but the necessary analysis estimates is simply not there. We get the same thing. A decomposition of the tangent sheaf. Yes, yes, yes. Even in the smooth case with our methods, we can do it. And I'm not sure there's any non-analysis way to do it. Known. Okay, he's sure that there's no non-analysis way to do it. Huh?
I mean, you cannot prove the Bogomolov. There's no proof for Bogomolov Boolean decomposition without using the Kähler-Einstein.
Yeah, so